Early spring break.
Hey, our next test isn't until Thursday of next week. Cool. You'll be here.
Of course.
Okay. Because we lost 2 days. With 2 days, you can just every time you see it, all right, it's 2 days out. Yeah,
So is that's the day before spring break starts, right?
that's right.
Okay. So not, okay, next Thursday, got it.
Yep. The day before the last day for spring break, that Friday. That worked perfect. I wouldn't want it to linger over spring break anyway. I know we think logically you think we get more time to study. Never works.
Study with a late
Oh, is it Friday?
It's like a late one.
Finals is a whole different story. You'll get ready for final. Just
What, Tampa?
Yeah.
hey, good afternoon, everyone. We're gonna do 5-3 and 5-4 today. 5-3 is we actually got into 5-3 a little bit in the last lesson, but we'll start right where we left off. They call this the multiplication rule for probability because it's probably A and B occurring. We just multiply the two events, but you can only do this if the events are independent. Don't let that phrase "independent events," intimidate you when you see that. But in any scenario, we can always think about it and go, are these events truly independent? If you don't think they are, please feel free to raise your point if you're reading a problem out of the textbook. But last thing I was doing was the roulette wheel, and so I thought I'd do another one. And the roulette wheel, you don't have to memorize this roulette wheel, but there's a total of 38 slots, and 18 are black, 18 are red, 2 are green. And we did this idea of, playing the game a few times. Well, I think we did 6 times last time, right?
Mm-hmm.
All right. Let's do 8. Now, this sounds crazy. I'm going to say, what's the probability? This is a little metal ball. The metal ball falls in a red slot 8 times in a row. All right. The probability that the little metal ball falls in a red slot 8 times in a row. That means 8 times consecutively. All right. In a row. Question mark. That means consecutively. Eight times in a row, 8 times consecutively. Play the game 8 times. Red, 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 red. So as you're copying this, is this or is this and?
And
You read this problem, and sometimes you have to put it in your own words. Because we're thinking, basically with the probability, basically we know we have these rules. But or, when we hear or, we think add probabilities. This idea of and probability, we think we have to multiply probabilities. Well, I don't see anything about an or and an in here, but if we put it in our own words, 8 times, we're like, I'm going to play this game 8 times. It's got to land on red, and then again it's got to land on red, and it's got to land on red, and then it's got to land on red, and it's got to land on red, and it's got to land on red. So this is an and this is that multiplication rule. And they're definitely independent events, everyone. The idea of independent events, if you need a refresher on that, it's the occurrence of event A does not alter the probability, of B occurrence. So just playing the games over and over I won't get better at the game, right? It's just like over and over and over again the same probability of getting it in a red slot. So what's the long way to do this problem? Well, for that first attempt, 18 reds out of how many slots?
38.
Something for the first event. But since I got to multiply them, and I actually like to write all this out because who knows, a student may like to write it this way, type it this way. Also, when you see it presented this way, it helps you remember it. It really does. All these got to multiply. That's first, second, third, fourth, fifth attempt. Here's the 6th attempt. I've got another 18 and 38 chance. 7th attempt, and then my 8th attempt. And they're all ands, so we're saying we're multiplying all this. Independent events. 1, 2, 3, 4, 5, 6, 7. And what's a quick way to type this on a calculator?
2 to the power 8.
18, divide 38, close your parentheses, and raise it to the
8 power.
8th power. Who's got the cool new calculators? You got one, right, Hal? You got math print mode? So math print mode, everyone, she has it like this. She hits this caret button on her calculator. It automatically puts a spot right here for her to put the number. And she'll just go like that. That means 18 over 38 to the 8th power. But who's got the old TI-83s? Mine's like a TI-83. What we have to type is 18 over 38. Actually, it looks like this on the screen. 18, we hit the division button, we hit 38, we close it, we hit the caret, and then we raise it to the 8th power. That means raise to the 8th power. So that's a fast way to do it. And yeah, you're encouraged to do it that way because I might mess that up. Now, do you get something silly?
Yeah.
It might be in scientific notation. Remember? Start looking for that. Very, very small probabilities are written in scientific notation. What's your screen say? I'd love to see yours.
Mine is different.
Yours is different, but I see a -3. 0.0025. All right. It wasn't in scientific notation. I do want to point out, everyone, if you start seeing numbers like this, I don't even want to round this to 1% because it's a lot smaller, isn't it?
Mm-hmm.
And what that means right there, if I just said that, that's 2 out of 1,000. Try it 1,000 times, do this. You might do it twice, right? Maybe. That's 25 out of 10,000 times. But you might start seeing numbers like this in this course. I like to write this number. 3.2, a bunch of values, and then E -5. Remember, that's a very, very small probability. It's in scientific notation. It means 3.2 times 10 to the -5. If you like to write that as a decimal, boom. How many zeros after that decimal point?
4.
4. Okay. 0, 0, 0, 0. Then I'll write the 3 and
2.
2. So you can see how small that is. So start on all these problems. You have purple vision. The whole screen. All right. Check it out.
Can you write like 3.2 times 10 to the power -5?
I love that. So and feel free to write this probability like this. You can write it like this. You can write it like this. I mean, that's a probability. In terms of probability, we'll never go over 1.0, right? Just don't write this, right? That means 320%. We're like, no, right? Not in probability. So be careful. If you got answers like that, we made that up. A good deal. Like, I'm curious, when I'm going to erase, can I erase all that? All right, I'm going to erase this. I'm going to leave this. And what we're saying is 20 times in a row.
Oh my god.
So that would be a what here?
20.
Maybe that'll do it. That'd be so small, the chances of doing that. Don't you agree? It's like, that wouldn't happen. I'm like, well, it could. It could. Yeah, watch out. Look at the chances of doing something like that. We're talking about a fair game, right? This game isn't rigged. For it to do red, and keep doing that. Crazy. So, I'm going to check out someone's calculator. Cool, thanks, Holland. 3.23, a bunch of numbers. 3.23, bunch of numbers after that, and that says E -7. Now, Michael, you can just leave the answer like that. I mean, that's a probability. But if you want to raise a decimal point, how many zeros?
6.
6. Good. I'll go 1, 2, 3, 4, 5, 6, and then a 3. And we're basically saying close to 0 chance, right? Close to no chance. That's what we're saying. Chances I win the lottery, right? Hey, so I'm going to start pulling some textbook problems from section 5.3. I'll make sure to put the problem number on the board. This is on page 284. This stuff's fun. Probably pretty cool. On page 284, how about number 13? It's titled Southpaws. Southpaws, I'm a lefty. Who else was a lefty? 1, 2, 3, there's 4 of us. I can remember this. Alright, we're the lefties, we're the southpaws. Well, let's see, they give the probability someone's a softball, just a random person. They said about 13% of the population is left-handed. Now, and that's true. About 13% of the population is left-handed. Alright, I'll just put that on the board. And the probability you got a lefty, a randomly selected person that they're left-handed is 0.13. Or if you want to write it like this, go ahead, 13%. 0.1. Alright. First question. I bet you crushed this. If 2 people are randomly selected, what is the probability that both are left-handed? I'll write that on the board. If 2 people are selected. Notice he said randomly. They didn't go to like a lefty club, right? Right. 2 people are randomly selected. Alright. They said, what's the probability that both are left-handed? Both are left-handed. The reason I wanted to write this on the board is because the wording. We gotta figure this out. Is this or is this and?
And
Hard, very good. I mean, we don't see it anywhere, right? I searched both. There's a keyword, both. Maybe that's the buzzword. It's like, here's the 2 people. This person's left-handed and this person's left-handed. We're looking at that probability, right? And so, all we have to do is take this and,
multiply.
that's probably the first person left-handed, and the second. And can we assume they're independent events? Yeah, I see this word randomly. Randomly. So there's randomly selected people, absolutely. It's like me going right on the campus. Just randomly selecting 2 people. Or the next 2 people walk down this hallway. It's like, hey, you lefty? The chances are small though, look at this. What's the chances of this?
0.0169.
I mean, does everyone agree this would be unusual? So for our class, we'll consider anything under 5% unusual. Sound good? Anything under 5% we'll think is unusual. Well, that's under 5%. This would be very unusual. Rare for that to happen. And you're like, really? Just 2 people? I know.
Is this like
Just
the
to get
standard deviation after 2 deviation is unusual? Same
Yes.
logic? Okay.
That's exactly it. And then when there's another question coming up, you'll get used to it. It's going to come out a few times today. I'll keep it this over and over again. You'll probably get tired of me doing it. The phrase, at least one. All right, so here you go. What is the probability? Tell you what, I'll put a yellow A right here. We still have if 2 people are randomly selected, right? Put a big box over there. All right? Right here, I'll put a little letter A. What is probably that? Letter B. So it's coming off this statement. So forget about both being lefties. Here's the question. What's the probability that at least one is right-handed?
So out of the 2?
Yep.
Also, then isn't that a complement thing?
You got it. Now, what I want to put in capital letters is this phrase, at least one. At least one. At least one. What's the problem with it? At least one. And then they said, is right-handed. You know what's in the book. I like to write this stuff out so you can see what's important, what are the keywords. The last one didn't have many keywords, but we put in our own words. We knew it was and. This idea of both. When you hear this phrase, at least one, get prepared to use, what rule is that again, Art?
Complement.
The complement rule. Get ready, what we're going to do is we're going to take 100% and subtract a probability. Because what we're looking at here, at least one is right-handed. And when that means this person's righty, right? Or, oh, here comes the or
This one.
that person's the righty. Or, there's another sscenario. They're both what?
Righty.
Righties. However, that seems like the long way to work this problem. Don't you agree? Because or means we've got to add probabilities, true?
Mm-hmm.
So it's like, man, that's going to take, I got to do the probability that this one's the righty. Add it to the probability that this one's the righty. Or, plus one more, add probability that they're both righties, right? Well, all probability, the probability of all events occurring have to add up to 100%, right? Which is 1.0. To quickly do this, it's the complement rule. We're just going to go, here's the answer. It's 1.0, 100%, minus the probability that they're both lefties. All right? Excuse me, both,
Righty.
right? At least one is right-handed. That means 100% minus probability, excuse me, both lefties. Sorry about that. We'll do this over and over and over today. Don't let this phrase, at least one ever scare you, intimidate you. We'll use the common rule. I'll go 1.0 minus the probability. And you know what's neat? See this part A, part B? It's usually set up like this, which is helpful. I'm just going to subtract out my last answer. Because what was the answer to my last question? What was the probability that they were both lefties? Which was which number?
This
Right there. This is going to give us the answer. If everything's got to add up to 100%, all possible, right? Possible events occurring right and left, or left and right, or right and right, or left and left, everything's got to add up to 1.0. The odds at least one of them's right-handed, which is like, well, that means they're not both lefties, right?
Uh-huh.
Do you agree? That means they're not both lefties, so 100% minus that. And this should be a very high answer because we get 1.0 minus 0.0169, which gives us,
0.9831.
thank you. There's a really, really good chance of this happening.
I got one question.
Really good chance. Art.
It's between two people, right? So
Yeah.
one will be left-handed, one will be the right-handed, right? So why are you taking the probably both of them lefties then? Shouldn't you take one as a righty, then shouldn't you separate it like 0.13?
Yeah, I'll write out all the possibilities. Let's write them out.
Okay.
Almost like this is our sample space. That's what they call it. Like, what are all possibilities right now, everyone? Let's use L,
And
L for the lefty and R for the righty. And
okay.
there's two people, right? Let's look at all possible scenarios. What's one of them?
LL,
Yeah, they're both lefties. What's another one?
LR,
LR. First person, second person. Give me another one.
RL,
And there's one more.
RR.
And what we did was, we just took 100%. Ready?
Uh-huh.
100% subtract that, and it gave us all these.
Okay.
Isn't that cool? Feel free to write this in your notes. We're taking 1.0 minus the probability of that event. Gives us all these possibilities, which is really high. Isn't that cool? It's called the complement rule. You go, you can always use it if you hear this phrase, at least one. Now, if you're curious about at least two and at least three as we go on, I like your curiosity. We'll get to that in chapter 6. So don't worry about that today. Why at least two? Or three? Like if you got 10 lefties, you want to know what's probably at least 5 lefties. That's for the remainder of this course, which is cool as well. Doing a great job at that. Okay, this is number 17 on page 285. There's that. A lot of you are like, yeah, but you put 17 as one of our practice problems. Every once in a while I like to do a problem that's actually in your practice list. We'll extend it though. We'll extend it. After I do 17, I'll make up another one. Alright? First of all, this is about 40-year-old males. And the probability that 40-year-old male lives another year. Randomly selected. So So P stands for probability. The probability that a 40-year-old male lives to be 41 years old. And everybody had the statistics on this from the National Vital Statistics Report, right? Do you think it's high?
Yep.
You think it's pretty good? Yeah, it is. It's pretty darn good. 1.99. This is for a randomly selected 40-year-old male, 757. I mean, that's really good. Hey, one number 18 is about a randomly selected 40-year-old female. That's higher. 0.998. Better chance, right? Hey, do you think it was this high 100 years ago? No. Very good. Do you think it's this high in some other countries? Very good. Very good. That's really good. It means you're statistically literate. That's really cool. So that was given to us. Well, what's letter A ask? All right, letter A. What is the probability that 2 randomly selected 40-year-old males live to be 41? What is the probability that 2 randomly selected 40-year-old males live to be 41? All right. Live to be 41. They live another year. I think, is this or is this and? All right, here they are. They're randomly selected. They're both 40. What's probably you make it another year and you make it another year. We're multiplying these, right? And they're randomly selected, so definitely independent events because they're just randomly selected 40-year-old males, right? I didn't go to what? The you know, this would sound terrible, but the club of, you know, people are being treated for cancer. You know, it sounds awful, but you'd be like, wait a minute, I don't know if that would be actually 0.99757 or something. So we're saying randomly selected. All right, 0.99757 times 0.99757. Or what's another way to type that?
Square.
Square. Some of you may want to do 0.99757 squared. I bet you this is still around 0.99, isn't
Yep.
it? So I'm going to write it out to a few places. What do you get? 99.
514.
See that? Stays pretty high. All right. You know, now in B, everyone, you go, what about 5? What's the probability that 5 randomly selected 40-year-old males? 5 randomly selected. So they're all randomly selected. I won't write that. 5 40-year-old males. 5 40-year-olds live to be 41. Okay, this time, everyone, I think I'll write it the fast way. 0.99757 raised to the 5th power, right? Caret 5, raised to the 5th power. It's probably still really high, but I'll go out to the 3 places again.
0.9879.
9879, I think I'll go to 3 places here.
988.
Right, or Autumn will do the 3 places. Yep, oh good, she's like cool. 988. And I didn't see the at least one yet, did you? Me either. All right, here it comes. And what's the probability that at least one? At least one. Now, they got to be clear here. They talking about the 5 people or the 2 randomly selected? They said a 5. So probably at least one of 5 randomly selected people who are 40 years old. So 5 randomly selected 40-year-old males. These are all males. 40-year-olds. What's the probability at least one of 5 randomly selected 40-year-old males? Everyone, the author wrote this. Does not live to be 41. Can I make that brief? I think they're using euphemisms here. Can I just say the word dots? Right? That's what they're saying, right? At least 1 of 5 randomly selected 40-year-olds. Dots. That's what we're hitting there. Does not live, they wrote. So, everyone agree a complement rule?
Mm-hmm.
We are at least 1.0 minus all 5 live.
Mm-hmm.
And I think we have that somewhere on the board. All 5 live. 1.0 minus probably all 5 live. And you look back to your previous answer. Be careful though. It's not that number. That wasn't for 5, that was only for 1. So all 5 living was the,
90.
see it right there? So I'll even circle this and bring it down here. I'm gonna go, you're coming, sneak through here, right there. And it's a 1.0 minus this 0.012, which gives me roughly, it's gonna be pretty high. 0.9, is that 88?
Mm-hmm.
There's the odds.
It's backwards.
Oh, 1 minus the,
Yeah.
Point- what is that gonna be?
0.12.
0.12?
Yeah.
Oh, so, thank you so much. I was looking, going, what am I doing? 0.988. 0.012. So 1 minus 0.988, giving us a very small chance. This would be unusual, wouldn't it?
Mm-hmm.
It's unusual. So 5 randomly selected people, and there they are, and they all met one day. And they're just like, yeah, think we'll make it one more year? Well, the chances that they don't are very small. Right? Very good chance you're all going to live another year. True? Hey, I wanted to extend this, because I didn't want you to think this was always very small. So how about this? I'll erase letter A, I'll erase letter B. Actually, I'll leave B up. I'm thinking of like a high school reunion. I mean, that's what I'm thinking of right now. How about a high school reunion? All male school, somewhere like the Matha, right? And let's just say there's 600 males in the senior class. So what I'm saying is, here's this reunion. What's the probability that 600 40-year-old randomly selected males live to be 41? Well, is that going to be as high?
You can try it.
Right? Let's see. That'd be 0.99757 raised to the...
600. So 0.23.
So it comes up?
Yep. Yeah.
What was after the 2?
2322.
2322. So what's the probability that at least one of those 600? See, sometimes this will happen. People are in discussion, you know, did you hear about Fred? Yeah, that's so sad. You know, Fred passed away and stuff. But it is shocking to people. But I want you to see, when you're talking about 600 males, 600 randomly selected males, the probably at least one of the 600 randomly selected 40-year males dies, this is not unusual.
77.
Because you take 1 minus the what?
0.23.
2, 3.
0.77.
We're saying, well, there's actually a pretty decent chance that that will happen. You follow? Walk on the probability. It's very interesting sometimes. We kept looking at 2, and then we looked at 5. We're like, well, what about 600? Right? Some gigantic reunion of 40-year-olds. That's like, well, there's a decent chance that one of them may not make it that next year.
When they do the quality assurance, like when a light bulb will fail and all, do they use this kind of thing?
Yeah, exactly.
Uh,
Exactly. And if you ever want to do at least 2, or at least, because it only takes 1 to knock the whole thing out, right?
Yeah.
So they use this. And the one about the light bulb, where is that? Number 16 has the Christmas lights. If anybody wanted to try it. Cool? Number 16 has the Christmas lights. String of 100 lights. Da 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 da. And they get letter B. What is the probability that at least 1 bulb will burn out in 2 years? Has that ever happened to someone? The 1 bulb will what? Yeah. Hey, well, great job with this. Love this stuff. Before we even get to that 5.4, I still want to do one more. It won't take that long. And when it's still on page 285, this is titled Cold Streaks. I just thought some of you might have a question on number 23. That's the reason I'm doing this one as well. I didn't want you to go back and go, all right, I got it. I got his problems in class, but I'm not understanding 23. There's something funny about it. And we're talking about players in cold streaks, and they're talking about a hitter who successfully reaches base 30% of the time. Any baseball fans in here? They call him a 300 hitter, right? They're saying his batting average is 300, but they're talking about that. In baseball, they like to go out 3 places past that decimal point. So there's that base. That's a good hitter. But I'll just chop that off. Same number. That individual, he gets on base, all right, 30% of the time, successfully. Reaches a base. Maybe first base, second base, home run. All right, 30%. So that's the probability that that player gets a hit. Gets on base. So far, so good? Now, they didn't ask this, but I wanted to throw it out to the class. I think you'll come up with this. So when that person's up to hit right now, what's the probability he doesn't get a hit?
0.7.
Yeah. Everyone agree? Complement rule? 0.7, 0.7D, you can write it 0.7. You can chop these zeros off if you want. 0.3 is 0.30, 0.7 is 0.7. Don't agree? Complement rule? All right, that's what's missing in this problem. They didn't write that. They didn't talk about that, because here comes the question. Cold streak. What's the probability that here makes an out? Find the probability that a hitter makes 10 outs in 10 consecutive at-bats. I'll repeat that. I'll write it on the board. Find the probability that the hitter makes 10 outs in 10 consecutive bats. You and I are going to put that in our own words, right? He's up the plate, out, and gets up the plate another time, out, and out, and out. This is and, isn't it? We're going to multiply these. So we're saying, what's the probability he goes out, 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 out. He just keeps getting out. It's called a cold streak, right? When's he going to break the cold streak? Man, 1, 2, 3, 4, 5, 6, 7. It just keeps. I mean, he's a good hitter, but this sometimes happens. All these probabilities.
So out means like no hit?
No hit.
Okay.
Yeah, I should be clear about that. Thank you. Probably getting an out in a baseball game, everyone was saying, he's out, or she's out. She didn't get a hit. Right? All right. Or by this idea, hit successfully on base, right? Successfully on base. I probably should have said that because can't they, get like a walk? There could be an error and it could reach it. All right, so we're talking about the probability of these what? These outs. This was the no hit. We're saying out. So which probability do we got to multiply to 10 times?
This one.
0.7. I just want you to be careful. Does that mean this?
No.
Sometimes we try to rush it. We're like, no, that's not what it means. We can either do 0.7 and multiply it 10 times, or what's a fast one? 0.7 raised to the 10. Or on your calculator, 0.7 here, 10. And then we'll talk about whether this is, typical, or is this actually something that would be unusual to happen. I mean, he's a decent hitter. Successfully gets on base 30% of the time. I mean, this would be the chances this person has this cold streak. Cold streak. What's the odds?
So that's not unusual.
What do you get?
0.028.
0.028. Everyone has less than 5%. I mean, it's roughly 3%, isn't it? That would be unusual, we could say. That's not usual. Someone in at least one hit. They're that good a hitter. But boy, there's so many factors involved, right? Maybe she, if it's a she, maybe she was injured. Maybe he was injured, right? Something like that.
So and is more binary. Either goes this way or that way.
That's right. That's right. As long as they're independent events. Here's another thing I want to get you thinking. Some of you may argue that maybe they're not really independent events. If you're a real baseball fan, you're thinking about pitcher versus what? Player, and sometimes some players better against this pitcher. Is the pitcher left-handed, right-handed? All that stuff comes into play. So you may make that argument, like, I wonder if they're really, truly independent events. Depends on, you know, how you look at it. So if we could say we assume this problem, we assume these events are independent. We'll assume they're independent events. Cool. All right, Edwin, great job at this. The rest of the class, we're going to do 5.4. This is conditional probability. All right. It is what it is. It means probability is based on conditions. So some of you already copied this. If you didn't, go ahead and copy it now. There's a vertical line here. So I'm going to read this from left to right. The probability A occurs given B.
So you mean like B occurs before A?
Yep, I'll say it again, Art, so you go with this. Probability of A given scenario B.
Okay.
What's the probability I die given that I'm a smoker? That kind of stuff, right? B is the event I'm a smoker. A is the event I die, right? What's the probability I die given that I continually drive my car 90 miles per hour down Route 50? You know, that kind of stuff. You know, things like this. But that's the given, so based on a condition, right? And this B event will be that given condition. So when you read it, probably A given B.
Okay, no, you just said it.
Oh, good. And you can always say A given B. The book uses like letters E and F. Might as well just use A and B, right? So that's notation, and this doesn't have an if statement. Do you notice that? There's no like if the events are independent. This thing, that's the true math formula for all events that are conditional. All right. So the first problem I'm going to go to is, this is on page 293. It's in 5.4, conditional probability. I got a frequency table here. Driver, passenger, I'll put down the problem number. This is problem number 19. 19. And you know I teach the midshipmen? Well, the plebes, I got plebes this year, they're all class of 2019. So if the number 19 just happens to come up with class, it's like a loud roar. It's like huge, like 19! Something, it happens like once, every 2 weeks. Number 19. All right, these are male. These are female. These are traffic fatalities. Okay. Traffic fatalities. Okay. The source, everyone, is the National Highway Traffic Safety Administration. Our friend used to work there, actually. 6,450. 11,856. 6,363. I do want to point out that's a frequency table, right, Ellen? A frequency distribution. We've seen these. And who's got the books? Two of you. I do want to point out there were other numbers given. I want to pretend like they were given. That way, nothing scares you, nothing gets you, nothing throws you off. There are other numbers given in this, Michael. Down here and over here and over here to the right and over here to the right, but I'm not going to write them on the board. All right. Letter A. I'm going to read it from the textbook. And then I want you to help me put this in our own words. That's what we got. We just have to be able to communicate this correctly, properly. It makes sense to us. This means probability of A, what's this again?
Given.
Yeah, just see that vertical line? Think the phrase given. Probability of A given B. Or these would be different events. Well, I'm going to read this to you, and it says, letter A, among female fatalities, what's the probability that a randomly selected fatality is the driver? Sometimes you got to reread it a few times. We're going to put it in our own words, though. I'm trying to think of, there's a given condition here, right? It was based on one condition. Like, was it all males and females? Let me read this again. Among female fatalities, here's this whole distribution of male and female. Among female fatalities, what's the probability that a randomly selected fatality is the driver? Well, I'm going to put that in my own words. Ready? What's the probability that the fatality is a driver, given that it's a what?
Female.
Female. Does anyone hear that? They said among female drivers. We said, okay, we're only thinking of what? The females, right? Is that what I agree? So you and I are like, I don't even care about this. I don't care about that number or that number. I'm only focused on what?
Female.
All that. So I'm going to write this out. Like a probability A given B. What's the probability? The given scenario is that it's a female. Well, let me reread it to you so you know what we put there. They go, among female fatalities, what's the probability that a randomly selected fatality is the driver? So here I get to put what?
Driver.
Driver, or fatality is a driver. You can just put driver. Fatality is the driver. Given that's a female. Now, when you may use that math formula here, but I think a lot of you do this through common sense. I'm being serious. You do this through common sense. Aren't we only looking at these numbers?
Mm-hmm.
Now, it's not on the board, but who thinks they know what the denominator will be?
Total.
The total, the sum of these, right? Right? Here's all the female driver fatalities. Here's all the female passenger fatalities. The total number of female fatalities is this number plus this number, right? Isn't that down here?
Yeah.
All right, so that'd be the total number of female fatalities. So what is this plus this? I'll put the number.
18,219.
So now I'm going to put it down there. When that's this added to this. That's the total number of female fatalities. Driver, passenger combined. That goes down here. Nothing about the males, right? And then what's up here? The
Fatality is
yeah. What's the number for the driver?
11,856.
Now what's neat, everyone, is do you notice something? I'm not putting probability over probability, am I? Cool. I didn't even look at that formula over here. But what's this formula say? Oh, it's the probability of A and B over probability of B, right? Well, weren't these weren't probabilities, they were just what? Weren't they just numbers? So when I want to point out, we can now extend this formula here and think, well then it's also, because did you see how you and I did this without that? And we didn't even need that. We just logically said total number of females, but in the top we put the drivers that were female, right? Conditional probability. Then if you want, this is interesting, we can write this formula also like this if you prefer. I would. Let n represent number of, because that's what we just did. It's like you and I invented that. Like you can just do the number of these over the number of these. What was the number of fatalities that was a driver? 11,856, right? What was the number that you had to total? 18,219. Hey, what's this come out to be? Yeah, how many total females were there, right?
60.
That's what we're saying here.
About
The total number of 18,219 females, right?
0.65.
Is that okay with that? Liz, you okay with this?
No.
Oh, now I'm going to go to the formula, because I did this without the formula. I did it without it. It was just logically you and I saying, okay, we had to look at the denominator had nothing to do with the males. It would have to be the sum of all the females down here. But in the numerator, we only had to put the ones that were what?
Driver.
That were drivers.
Right, this side makes sense, I'm trying to compare the
Oh, so she wants to use the formula. I'm with you. Ignore the formula if it bugs you, because you make sense of this, but I would like to explain it to you. But I think it'd be easier with this, because we're not going to use p's, because you notice we'll just think number of. So ready? What's A event? What's event A? Fatality is a driver. You go, well, what's B? B event is all females. So what we do is we go, for this number, if I used a formula, I'd be like, okay, I gotta write the number of people in that chart that is driver and a female. I gotta find that in the chart. And then the denominator, I gotta put down the number of all females. So you go, what's the total of all the females? We go, oh, we had to add that. Liz, very good. And then what was the number that were drivers and females? Drivers and a female, the 11,000 what? 856. And Liz, I'll be honest, I'm proud. I'm actually happy that you prefer just saying, I understand how to get the answer. That didn't make so much sense. That's common. So I want to ignore that thing if it's bugging you. I'm serious. You're just like, we understand the question, we go into a table. Letter B. Try this one out. What's the problem? Oh, let me read the book. And you and I will put it in our own words. Sound good? Among passenger fatalities. Okay, you and I are thinking this now, right? Among passenger fatalities. Okay. Here's your given scenario. Among passenger fatalities, what's the probability a randomly selected fatality is a female? So can I erase letter A? There's letter A. Let me read it again. This is going to be letter B. I don't need that number anymore. Among only the passengers, what's the probability that a randomly selected fatality is a female? Now I'm going to write that like this. They said among the passengers. So guess what's the given scenario?
Passengers.
Passengers. Only the passengers. What's the probability? They said a randomly selected fatality is a female. Okay, fatality is a female. And Liz, I think let's do it without that form over there. What's the probability fatality is a female? Given that it's a passenger. Given that it's a passenger, it has to be a what? Passenger. We're only looking at what? All passengers. What do you think goes down here in the denominator? I would have to total all the what? Total all passengers. Everyone agree? Which isn't in the table that I didn't put because the book gave it, but I pretend like we didn't know it. You'd have to add these. What do you get?
12,000.
12,816.
Thanks, Liz. That's the denominator one. 12,816. Total number of passengers. So total number of those. Oh, I see it in the formula now. Yes, the total number of those. Right. All passengers. And then, of course, what goes up here?
Female.
The passengers, right? Fatalities that were female. There it is. All right. What's that around? Let me get the decimal.
0.496.
496? 50%? I'll write 496. But yeah, roughly 50% chance. Alright? Given it's a pass. Given it's a pass. I want conditional probability. Liz, I agree with you too. It's like, yeah, it makes sense. This can sometimes make it complicated. So if you're able to do those two probably like, I didn't need that formula. Please don't use that. I'm being serious. Like, we understand it. Conditional probability. It's based on this condition, so it limited our what? Denominator. Like, it was only passengers. We didn't consider the what? The driver numbers. Yeah, conditional probability. Cool. Hey, in my next problem, it's going to deal with the cards. I especially encourage you to try this problem with the cards without looking at that.
Okay.
I think, this is my opinion, Liz, I think when people try to do this question with this, they get more complicated and they get thrown off and come up with a different answer. So I want you to just think about the actual, just keep it, like use your common sense to go, all right, logically, this is what I have, and this is what would be in the numerator, this would be in the denominator. If they say a given scenario, that means that given scenario is that denominator, right? The total number for that given scenario, right? So if they said, hey, given that people have white shoes, you're like, okay, we're only considering people that have white shoes, right? And that's the total number of people have white shoes in the denominator. All right, so here's the question. Everyone? Cards. How many cards in a deck?
52.
52 cards. How many cards are red?
26.
Half the deck is red, half the deck is black. I do want to point out 2 red cards are the diamonds and the hearts. So we do have to have knowledge of that before we do the problem. The black cards are the clubs and the spades. All right, so here's my question. I'm going to select one card. What's the probability that I select a diamond from the deck? Given that, this means you know, you have knowledge of this. Given that the card is red. And I encourage us to look at this problem. We're going to answer it. It's not easy. Michael, let's ignore that. First of all, what's the given scenario? If you wanted to write it with this stuff, we can. The given scenario is the card has to be what?
Red.
Red. Well, we're looking for the probability it comes out to be a what?
Diamond.
Diamond. So am I counting any of the black cards?
No.
All right. Let's say the bottom half of the black, they're all out. They're out. Only the red cards. Want to see this? Given the card is red, so I only got red cards now. Only the red. See how it's not nearly, it's not the full deck anymore. And I'm going to come up with my fraction. This denominator is not 52 anymore, is it? What's the denominator?
26.
26, I love it. We don't need that formula over there. 26 red cards total. Because you said, given that it's red. If they told us given that it's red, it has to be red. There's no black cards in this, right? 26. Now, how many diamonds are in the deck?
13.
And we just got to remember how many diamonds there were. Do you remember in the total number of this, there were 13 of these, there were 13 of these, totaling up to the what? 26 total red cards. So the top number is going to have to be a 13. Now that's a great answer, but I think we could reduce that. What's that?
50% half.
Half, or I heard 50% or 0.5. Oh, love it. I don't list, so I put a problem like that on the test.
Yeah,
I get 25%. A lot. Yeah. I'm telling you. Yeah. Taylor, I did it. 25%. I think what happens is they try to get in here. And they get in this, and they see the P's, and it gets a little messy, and right? So I encourage you. We can still look at it. It's like, all right, that was the number of the red cards. That were the numbers that were red and diamonds. I mean, if you want to look at that phone. Number of red cards, 26. Number of red and diamonds, 13. If you want to look at it that way. Cool. Awesome. Hey, great job with that. And when I put something else on the board, if you didn't copy, go ahead and copy it now. If A and B are independent events, then the probability of A given B will simply only equal the probability of A. Now I want you to see where this came from. All I did was take this formula right here, right? And I substituted right here this part for this. It's in the book. So if that was substituted here, can you see what would cancel?
B.
So I just want you to see why. I wonder if you're curious where this came from. Why is this true? Well, I took the probability of A and B, was there, and I divided out the what? The probability of B, and what cancels?
B.
Does someone say that? I mean, that's what's going on here. I took, what's key is, for your notes, this one and this one both had the phrase, if A and B are independent events. This one alone, though, had no statement like that, right? So, if A and B are independent events, what has to be true? Probability of A given B must equal the probability of A. Cool? Hey, would you make a note? I know there's like 3 things that are not on that formula sheet. This is on that formula sheet, this is not. So that's something, would you remember that? Would I remember this one little key statement? I think you will. Just go, oh, it's just going to be this probability. If the events are independent, that means one's not dependent on the other. Does not depend on B. A does not depend on B. It'll just be the probability of this A occur. Cool? So I'm going to go to a problem out of the book. I'm going to do number 10 from the textbook. It's a long statement, and all you have to do is say yes or no. But afterwards, when we explain why, all we're going to do is reference this. The question is about whether or not 2 events are independent. Cool? It's a long paragraph. No worries. We're just going to say yes or no. That's it. But hey, if A and B are independent, what has to be true? This probability will have to equal this probability. So here's this long word problem. We're just going to have to listen to the word problem, write keywords down. We'll make sure we'll come up with that and that. But we're going to keep it simple. We're just going to check to see if the probabilities are the same. Right? I mean, you know what I can do with this statement? I can actually reverse it and put knots on both of them. So you know what's going to go on? Is this true? If the probability, or A given B, is not equal to the probability of A, they call this a contrapositive. I don't want you to get so worried about mathematics. Have you heard of a contrapositive? It's where I switch these around and I'll put knots. See the if and the then? So I'll say, if probability A given B is not equal to probability A, then the events are not independent. But that's what you and I are looking at.
So they're dependent. That means.
Yeah, he knows they're dependent. Are not independent, as you said, dependent. There's some dependency. It depends on this. Cool? So I want to keep it simple. If these 2 numbers are not the same, the question is, are the 2 events independent? And I'll give you the 2 events for the problem. I'll read you the 2 events. Paragraphs coming up, everyone. But would you keep this problem simple? This is going to be number 10 from the textbook. It's in 5.4. This is actually on page
292.
292. Are the events independent? Yes or no? If these 2 numbers are not equal, do you agree we're going to say no? Look, to be independent, so if these 2 probabilities we get out of this problem are not equal, we're just going to flat out say what? No. No. All right? No, because that's really what we're saying here. If these aren't equal, then they're not independent. No, they're not independent. So here's the question. And as I read this stuff, we'll jot some stuff down. The probability that a randomly selected individual in the United States, 25 years and older, has at least a bachelor's degree is 0.279. Oh, we can abbreviate that. Want to put some notes? Probability, bachelor's degree, 0.279. You can write, the reason they said at least 25 years old, everyone, do you think like 5-year-olds have bachelor's degrees?
No.
So they looked at only a specific age and older, right? They said, oh, it's like a 25-year-olds and older, and they said, all right, but the probability that a randomly selected individual in the U.S., 25 years and older, has at least a bachelor's degree, so they can have a PhD also, but here's the odds. Randomly selected, 25 years and older, about 28% of the population has at least a bachelor's degree. Okay, got it. Here's the next statement. I'm going to bang on the table too, so I don't want to scare you. The probability that an individual in the United States, 25 years and older, has at least a bachelor's degree, given that the individual lives in Washington, D.C., is 0.485. Okay. So probability you got the bachelor's degree. Given that, they live where?
DC.
Live in DC. Is actually 0.485. All right. So here, these two numbers, the only two numbers given in the problem, the two probabilities. Probability bachelor's degree, 0.279. Probability of a bachelor's degree lives in Washington, given that they live in Washington, D.C. 48.5%. All right. What's the question? Are the events having a bachelor's degree all right, what's the other event? Are the events having a bachelor's degree and the other event lives in Washington, D.C. Are these two events independent? Right? Well, if these two probabilities aren't equal, we're going to say a big flat, look, not independent. We're going to say no, right? Are they equal? No. Big ol' what? No. And would you keep it simple? Like even in the test, once you read through that long word problem, if those two probabilities are different, you're saying what? No. Everyone got that? I'll say it again. You got these two probabilities are different? No. No. Boom. Okay. Be independent. These would have to be equal. There's some dependency here. Now, explain why. Right? I don't have to write a long paragraph. All I have to do is this. There's my theorem. I see it right there. I just have to write the probability of bachelor's degree, given that they live in Washington, D.C., is not equal to this probability. There's my explanation. I don't know if I'll write explain on the next test. I used to write it. I mean, students would write like 2 pages of stuff. And I read through the two, I'm like, they still didn't state it, you know? Because in math, we got to reference like a theorem if we got to justify something.
Can I ask a question?
Sure.
Say probability of bachelor's degree is 0.279. And probability of bachelor's degree living in DC is also 0.279. That time, do they become the dependent?
That's a good question. I'm going to say this as a mathematician, statistician.
Uh-huh.
I still don't think we have evidence that we could truly say they're what? Independent. We're saying it here in this theorem.
Uh-huh.
We're still saying, you know, there could be just chance that they came out the same and stuff. But yeah, you could assume that there is, you know, independence there.
Well,
Hey, I was wondering if someone knows why. Why did this jump so high? DC, why DC?
it's more money.
Well, what's going on in DC? There's a lot of what kind of jobs? Think
Federal-
DC, think
federal-
Northern Virginia, what is it?
Federal jobs,
Yeah,
government.
federal government. That's why, that's why so you go, what's going on here? Right, it's all these government jobs. So we're saying here, probably you have a bachelor's degree, given that you live in DC, well there's so many government jobs, and that's why that's so high. Cool. Hey, last thing we're doing is have a little fun. Oh, question, go ahead.
Could it also be higher because it's like they're making the sample space smaller? Because like when you were saying about the left hand how the it was gonna be, what did you say, it was gonna be higher or lower?
Yeah, I got you.
Smaller group of
Yep,
people.
with a small group.
Yeah.
Yes, funny thing, in small samples anything can happen.
Right.
Anything, but then as you get towards the what? Larger and larger, it's gonna go towards that. You're exactly right.
Okay.
The law of large
I mean,
numbers.
I get what you were saying about like the federal, but I just didn't know if that was on the too.
Cool.
Okay.
Very good. Hey, last thing, and we're just gonna have, it's only gonna take a second. How many got here? How many total? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 23. And when we're gonna look at the probability that 2 people will have the same birthday. Cool? All right. I'm gonna say at least 2. Last problem. Share a birthday. This will only take a second, everyone. But this is my favorite problem. They call this the birthday paradox probability problem, because it is a paradox. I mean, how many days in a year? We won't consider leap year, even though it's leap year. How many days in a year? 300 what?
65.
65. And right now we got about like 23 people. We got roughly 23 people. So you might be thinking the odds that at least 2 people share a birthday. Not to be the same year, just the same day, but you know, we might think, oh, it's just probably this, right? No, it's way higher than this. we're going to find out right now. First of all, see the at least 2? Well, that means the Complement rule. One minus probably that no 2 people shares a birthday. Okay. Like I said, I'm not going to keep you up. This won't take that long. 1 minus probably no one shares a birthday. That's how we're going to attack this. Cool? Now, here I'm going to start out. Everyone, what if there's one person in the room? Well, there's a 100% chance that no one shares a birthday. Do you agree? If there's only one person. Well, what if there's now a second person in the room? Well, there's a really good chance that this person does not share it with this person, which is 364 out of 365. All right? That's the odds that this person does not share it with this one, right? Isn't it really good? It's like me and, all right, it's like, what's the chances we don't share a birthday? That's really good. But then the third person enters the room.
363.
And you all see a pattern to this?
What's the factorial?
And I have to keep doing this, but for how many people did I say? 2 people share a birthday. There was 2 people I have to mention out of, I looked in the room and we got, including me, 23 people. So 2 people out of 23 total people. Cool? So I'm going to have to keep multiplying this. That was from the first person, second person, third person. But I'm going to have to keep doing this. So I'll put dot, dot, dot until I get to, if you're curious, what would be the 23rd person? That would be, you got a calculator handy, what's 365? I want you to subtract 23, but then I want you to add 1 to that. So that'd be what? 340, but then add a 1.
343.
And I want to tell you why. You go, why'd you add a 1 to that? So I get 343. The reason is, because everyone just think about this. If I just did 3 people, what's 365 minus 3? 362. Look what the third person had. So it was 1 more than that? So I have to do, for this one it would be that minus that. Well, to get this, there's an easy way to do the denominator on the calculator. Isn't that 23 365s multiplied together? But I want to give you a cool button on the calculator that does the numerator. What would do all this numerator math right here fast on the calculator? There's a button called NPR, and I'm going to hit that. I'm just going to hit 365 NPR 23. It's called a permutation button. And I'm going to do it right now, so I'll hit the light and check out the odds. You're going to love this one. This is cool. Ready? One. Clear. 1 minus. All right, I'm going to type 365. I'm going to hit the math button. I'm going to arrow over to PRB. Everyone see PRB? And then number 2. And then I'm going to type that 23. Now I have to divide out what? So that's 365 NPR 22. It means 3D, that's a permutation formula. And I divide out 365 raised to the 23. Okay. Look at the odds. This is why they call it a paradox. Can you believe this? And what's the odds that at least 2 people right now in this room share, I don't know anybody's birthdays.
51%.
Except for, I know McGarvey's, but she's not in there. Oh, and I don't know anybody's birthdays. So as you're about to pack up, can we go around the room, say birthdays, see if, what's the odds this happens?
51%.
There's a pretty good chance, like 50-50 chance, 2 people want to share the birthday as you pack up. I'll go around, if you don't want to tell everyone your birthday, would you just make up a day like, September 8th or something like that, right? I'm going to go first. Come on, I'm hoping this happens. We got a 50-50 chance. I'm first, April 7th. Oh, it had to be you though. All right, well, we'll keep going. Might still have Art.
July 17th.
July 17th?
Yeah.
November 24th. October 13th.
March 20th.
Come on, it's going to happen.
June 30th.
Your birthday's coming up. June 30th.
December 4th.
December 4th.
December 6th.
Ah!
January 7th.
January 7th.
November the 12th. August 31st. June 7th.
Wait, what are you?
June 7th.
June 7th and April 18th.
January 11th.
October 23rd.
October 23rd. August 31st. Uh-oh. We got what? 7 remaining. Here we go.
November 10th.
January 26th.
October 7th.
April 18th.
2 April 18th. That's it! Yes! Yes, it happened! No, we got right at the end! April 18th! Woo! October 1st? February 3rd. It happened! Yes! Oh, I love it. We had a 50-50 chance.